Okay, so in renewable energy, we need to talk about energy loss, energy gains, and how we balance systems and we manage power. So let's just talk about renewable energy, um, basic electricity. And one of the things that we need to do is we need to talk a little bit about where um, everything came from. So back before there was electricity, the world had animals, and there was a horse. And this is a bad photo of a horse, but we'll just make a basic horse, and then we'll draw this horse here. And it's got a nice tail, it's got a mane, an eye. So one horse looks more like a lizard. When electricity came out, they had no scale to measure it, and so they started making motors, and they re- they related everything to 1 horsepower. And over time, things got an equals multiple horsepower, so it could be something like 100 horsepower motor, or a um, a 2 horse um, a 2 horsepower light. It's a little bit odd when you think about lighting and horsepowers. But 1 horsepower, HP is the terminology, equals, um, it's like 1,000 watts. It's close to it. And a watt, 1 watt, in there, it's got a mathematical formula. So if we say equals, if we say the volts times the amps equals, amps equals watts. So we can take these numbers here and we can find out um, what our watts are um, when we work in electricity. So let's talk a little bit about where we're going here with watts, volts, and amps. And I'm gonna erase this real quick here, um, and we're gonna go and move on to the next subject. So hold on here. Just erase all this. And if we go to electricity, think of electricity as um, if we have let's say there's a traditional power plant that um, it may burn coal, or it may be a nuclear power plant. And let's say your home is over here, and we need to um, turn on a, a, um, a, a charger, or excuse me, let's just say you're going to wash your laundry, and your washing machine. Let's just see here. That washing machine consumes probably like 1 to 2 kilowatts per hour, and it's gonna um, we're gonna send electricity through the wires, and we're gonna send it into this house, and then inside the house we're gonna feed electricity through the machine, and then what happens is we want to go essentially to ground. So there's a ground symbol that looks like this, and if there's a pump in here, or something that's spinning, let's say it's pumping water, the positive electricity, just make the positive electricity in a different color, make it blue. We'll say it's got positive electricity flowing through this wire over to the house, and it comes into the breaker here, and then it goes into different things like light bulbs or a washer and dryer, and it goes through this motor here, and it's trying to ground out. So as it heads towards the ground, it's pulling. So we have this pulling effect where it's pulling it towards ground. So in electricity, you have positive, and then you have negative. And positive usually comes from a source, an energy source. And negative is where it's going to ground. And so like when you have like planet Earth here, and here's all these continents, and we have the sun right here, and the sun is putting out positive electricity that's in the form of particles, and it comes to planet Earth. Planet Earth is negative, so we've got negative here that goes to the ground. And so when we think in terms of making electricity, we want to push positive electricity, and then we want to pull negative. So it's a push-pull type of environment. So let's move on to the next subject, and we're going to let me get rid of all this, and we're going to talk a little bit about something that goes way back in time, which is AC and DC, direct current. And so when we talk about alternating current, AC is alternating. Oh, my phone keeps going off here. Alternating current. And DC is direct current, direct. And the difference between the two is, let's just change colors here, and we'll go to like that color. An AC curve, power curve is like it's a wave. It's like in the ocean. And so we could put a negative ground over here. So that's ground. And this could be the source. So this could be a power generator, or a solar panel, or water turbine, or something like that. And AC can go long distances. So we'll just put a thing here that says long distances.
Sorry, I didn't quite.
Long distance. So they're really good at long distances. A couple other things, but and then if we switch colors here and we go to like this color right here, and let's just make this a little bit bigger. But when we talk about DC, it's a square wave. It goes up and down. It's on or off. And where you see a lot of DC being used, and it only goes short distances, so it's got its own benefits. But if you think about it, again, we have a negative, a ground, and we have positive over here. And so DC current, electricity, it's used in like cars, automotive. It's used in solar. It's used in computers, and so forth. And if we go back to like the AC, AC is electricity. It's used in like transmission lines. So transmission lines because it wants to go far. We can use it in. We can use it to for heat. We can use it for motors, all kinds of stuff. Motors are kind of interesting because they can use both AC and DC. So a motor, let's just make a picture of a motor here, and it can be both AC and DC. Okay, so let's move on and we'll talk about wire sizes. I'm going to erase all this. So one of the things that we do when we're trying to figure out how we manage power, we have to think about the voltage and the so we're going to, when we look at power, both AC, we'll put AC, whoops, this, okay, we talk about AC power, I'll put a table over here, and I'll do DC over here. AC is used to make power, and DC is both make and use. So both of them have the same way of talking about energy. They're both equal. So we have, in AC, we have volts and we have amps. And in DC, we have volts and amps. Okay, so back at the earlier section, a watt equals volts times amps. And a watt equals volts times amps. So a volt is the speed, how fast the electricity is going. So let's go speed. And amps is the quantity, QNTY. So this is speed. So if we go into calculate, like let's say we have, oops. Okay, let's say we have some solar panels. And like I said earlier, the solar panels all make DC power. So let's say this solar setup is 6 solar panels times 1,000 watts. So we would have the capacity of making 6,000 watts of power. So what we need to do is we need to make everybody talk together. And so let's say there's like a tree hanging over and there's shade here. And these are getting more power. We have to get everybody talking together. So we're going to set the voltage. We're going to set the voltage. And the voltage will be, let's just say like 36 volts. So everybody has to get stepped up. So they all have to go be adjusted to adjust up. So when we think about this, let me just erase this. We can find out what the current is of each one, the amps, by looking at basic math. So we'll say, let's say we go watts equals volts times amps, right? And let's say we have 6,000 watts equals And we know that the voltage we were going to set for 36 volts times A. So, so the amps, we need to know how many amps we're going to be pushing to size our wire. So we can just basically divide by 36 and divide by 36 over here. And if we look at 36 into 6,000, let me do it on my calculator here, divided by 36, that's 166 amps. So, so the watts, so 6,000 watts, oops, 6,000 watts at 36 volts uses 166 amps. That's a lot of amps. So what we have to do is we have to take like a wire and figure out what the wire diameter is to be able to handle this much power going through here. So this is like the plastic sheathing. And then here's like the copper wire size. So one of the things about wires is it's about the diameter times the length. So we can put this into a formula and we can say 36 volts over 166 amps equals a certain diameter and length of wire. So we're just going to leave it here at where we're at with going in to calculate wire sizes. But I wanted to just try to help you understand AC power, DC power, why we use them, what the benefits are, where you use them, and then how you calculate your volts and your amps based on the watts and based on horsepower. So we can go back to horsepower, and if we look at this right here, the 6,000 watts, how many horses would that be? Basically 6 horses. So we have 6 horse. And so that, a lot of times, the motors are rated by horsepower. It goes way back in time. So we would have a 6 horsepower motor that we would be supplying power. So at the end of the day, you can kind of use basic math to go back and forth and calculate what the load sizes on your alternative energy play is, and then figure out how many solar and wind panels and water turbines and battery packs are needed to support certain energy consumption scenarios. So anyhow, that's where we'll leave it. And thank you very much. You get a big happy face here at the end.